Okay, so the rate equation, including the effect of non-Darcy flow, sketched here in red, shown here in the second plot. How do we handle this BQ squared term using a log back pressure graphical analysis? So I'm going to show you how that's going to work. So the general rate equation with non-Darcy term. So if you take that equation and plot I'm going to actually add so okay. So I'm going to put in how this curve will look. If you go to low enough rates, the DQ or the BQ squared term becomes insignificant. I mean, let me just rewrite the equation here. So delta pressure squared, PR squared minus PWF squared is equal to BQ squared plus AQ. And in the limit of QG going to 0 or to some small value, that basically approaches AQ, right? The QG squared term becomes less important. So at low rates, you're going to get effectively this slope of 1, okay, at low rates. But as the BQ squared terms, as the rate gets higher and higher, what's going to happen is that you're going to get larger and larger pressure drops. And I'll just sketch in kind of what would happen if you didn't have non-Darcy effect. Okay, so that's going to be no non-Darcy. Another way of saying that is that it's Darcy only. Okay? But what actually happens is that this thing starts curving. Like that. And as that rate becomes really large, the BQ squared term dominates. So in the limit, as QG gets very large, then the delta pressure squared go towards BQ squared, right? That's the pressure drop. And in this case, the slope is equal to 1. But here, the slope is going to be equal to 2. Because when we take the log of that term, the 2 is going to come out and you're going to get 2. So this slope here the limiting of that slope approaches 2. So this is the generalized equation, and you basically have this transition from slope of 1 to slope of 2. Now, I'm doing this by eyesight. I mean, but that's what you end up getting. Okay? Yeah.
You mean in a very high rates, the effect of AQG is negligible compared to BQG?
That's right. That's right. Yeah. When the rate gets large enough, the QG squared dominates. And when the rate's low enough, the QG squared is insignificant. Yeah. So that's kind of the bounds on the shape of this. Now the other thing is that for practical purposes, when you get a new well, it comes on at 10 million cubic feet per day, let's say. Okay? And it's the real economics, when you're really making money from the well, is when the well goes from making 10 million cubic feet per day down to 500,000. The range of rates where the well is really economic is seldom more than 1.5 log cycles. Okay? It's not like it goes from 100 million to 0.1 million. It doesn't do that. I mean, so the range of rate of interest will seldom be more than about 1, at very most 2 cycles of rate. Okay? And these people in this, well, here's the book. I'll send it around. You can look through it. This is Mike Petkovich's original copy. This was when he started working for Phillips in the 1950s. This was the book he was given. And you can read through it, look through it. But that book was written in 1935. Okay, so they were using back pressure plots and this kind of analysis a long time ago. And there's a lot of data, measured data in there as well. So the thing is that they knew there's, the Forsheimer equation, the quadratic was the theoretically maybe the most valid. But as a practical engineering tool, what they knew is that over a range of about 1 to 1.5, maybe 2 cycles, that curve behaved almost like a straight line. Okay? So what I'm going to do is I'm going to plot the red line. I'm just going to say that we start here at 10. and we go down to here, in this range here, and through that range, I'm going to draw a straight line that looks like that. Not a very good straight line, but I mean, the most important part of the straight line is up here. So what I'm going to do is I'm going to try to draw it through here. Something like that. That's a straight line that it's going to be off down here low, but it's through most of this it's getting it right. So basically we assume we approximate with a straight line. And that straight line will have a slope, okay, somewhere between 1 and 2. And the equation describing this straight line, the approximate equation describing the straight line, the approximate log straight line model is QG is equal to C PR squared minus PWF squared to the power n. Okay? Where the slope on that plot is just equal to 1 over n. So that means that the n will be varying from 1 to 0.5. Okay, here we have Darcy-like. Here we have basically this BQ squared domination, or highly non-Darcy. Okay. So BQ squared is the dominating term. Here AQG is the dominating term. Okay? So if you make measurements on a well and the slope from the multi-rate test has an n of 1, then it's suggesting that this first 1 to 10 meters of non-Darcy effect is negligible. But if we make it a multi-rate test on a well and the slope is 0.6, then it's suggesting that there's a lot of effect of non-Darcy flow near the well. Okay? So this, you just measure from the multi-point test, and that's what his paper is about. You plot up the data on a log-log plot, you look at the slope, and the slope being closer to 1 or being closer to 0.5 identifies the importance of this non-Darcy effect. Okay? Now this C is not the same. This is not this C here, which I'm going to call C R. For the reservoir okay. It's not equal. Well, it's related to this KH over temperature log ERW minus 3/4 plus skin. It's related to that, but it's only equal to that if, well, since we've got the pressure squared, you also need a mu z here. Okay? It's only equal to this if n is equal to 1. Okay? Okay, it's related to this, so it's clearly its magnitude is related to the term, but it's only equal to this if n is equal to 1. Okay? And if n equals to 0.5, which it essentially never is, okay, then that CR would be just equal to the one over the square root of b. Okay. It's only equal to a, which is what that term is. Or would it be 1 over a? I think that'd be 1 over a. If n is equal to 0.5, then that CR would be equal to 1 over square root of b.
So,
Yeah.
so if we want to decrease the effect of this non-Darcy scheme,
Well, if you want to reduce the effect of the non-Darcy skin, you have to change the rock. It's effectively a rock property. Now, in theory, driller's damage can magnify the beta. Okay, it can magnify the effect of the non-Darcy term. Okay, so if you're able to clean up some of the driller's damage, then that S could go to 0, and the value of B could also be altered because they're kind of related. I mean, the beta, D is proportional with beta. Beta is proportional with 1 over K from measurements. So if you lower the permeability in the first meter, you're increasing the beta. You're making the D bigger, you're making the B bigger. Okay? If you remove that damage, the beta goes down, the D goes down, and the B goes down. Okay? So, but it doesn't disappear. So
but if we assume that there is no driller damage,
then you can't do anything.
we cannot do it.
Well, not
By
really.
changing the choke or making the rate of gas not that high, by
Well, but if you lower the gas rate to get rid of the extra pressure drop, you don't produce as much gas. You can't. It's like saying Darcy's permeability. You can't really do anything about it very much. It's a rock property. If you mess up the rock, you can try to clean up the rock. You might be able to stimulate the rock a little bit to get a higher permeability, but if the beta term, the BQ term, if n is less than 1, it's going to be that way. Now, as the well goes into late depletion, as the well rate goes down, because of time depletion, the effect becomes less. I mean, it does leave the red curve. It's getting better here, right? But other problems, you get other problems. That's why using the curve like this is. Yeah. So this is an approximation. It's used extensively in the literature and in engineering, at least until 1970, into the 1980s. It's not used very much anymore because we can solve a quadratic equation very easily. But it's discussed in the Fetkovich paper. It has historical significance, and it's a diagnostic. It's an easy way to find out whether this effect exists. So, okay. Now, I think in the paper, if I can find it, I'll see a comment. Oh, I got to reverse this. Somewhere here it is, this table here. This is just example from 5 big gas wells in Phillips Petroleum when this paper was written in around 1960 something, I think 70. And what you can see is the back pressure slope. It's not really the slope. It's the N value. Okay, is close to 0.5 on these first 3 wells, and it's very close to 1 on the last 2. But you see the level of permeability here. And he makes the statement somewhere in here that generally speaking, this effect is most important for high permeability reservoirs. The reason for that is what you see is that you're making really big rates, 88 million, 68 million from these 2 wells, where there's just looks like there's Darcy effect. But where that's coming from is that these are very thick formations. They're very thick formations. So the velocities just don't get that high. These are high permeability but thinner formations. So they make really big rates but through a smaller section. So the velocities are much higher. Anyway, that's something that it's mentioned somewhere. I don't know where he talks about it, but okay. Okay. So let's see here. Okay, so I think this is pretty much where we need to get. Okay. Just trying to think if there's anything else that I think that's mainly it. Okay, so now we can go in and talk about the second part of the paper, and that's basically flow and pipe flow. Okay? And the first type of pipe flow that he talks about is in tubing, to get the gas from the well bore to the surface. And the second type is pipeline, or gathering line, maybe more appropriate. So you got this production tubing inside the casing, formation, perforations into the rock, and there may be a gathering line to take it to the pipeline, the bigger pipeline here. The diameter of this gathering line conceivably could be larger or smaller even, to connect into the major pipeline. So this would be our gathering line. It could be shared by other wells, but for convenience of the analysis, we're going to just say this well is being gathered into the pipeline here. And we're going to look at the different pressures here. Let's say this is our no-flow boundary. So gas over here is flowing towards another well. This is our bottom flowing pressure. This we refer to as the flowing tubing pressure. I think we've already talked about this. This is the flowing pressure in the annulus. We call it PW. At least that's Fetchkovich's nomenclature. So this is and then for the purpose of what we're going to talk about in class, I'm not going to bring in the gathering line part. Okay, it's now what you can say about pipe flow as a first order model of pipe flow is that if you ignore gravitational effects. So we're basically saying that flow is horizontal, or we're saying that flow can be vertical, but we're going to be using, we're going to subtract away the pressure drop due to gravity. Okay? Either way. So if you ignore gravity, another way of saying that is that you only consider friction, then what you can show is that gas rate is given by a very simple equation for pipe. I'm going to write C for the time being, that the pressure going into the pipe squared minus the pressure going out of the pipe squared to the power of 0.5. That will get you first order right in any pipe having gas, even if it's carrying with it some liquid and I mean, it's first order that this is Mother Nature. This is the way it works. Okay, gas rate, this is in standard cubic meters per day or standard cubic feet per day. And these two pressures, all that matters is that they're at the same elevation. That there's no reason that there's a difference in pressure because one is here and another was higher. Okay? This is fully turbulent flow. We almost never have laminar flow of gas in pipelines. It's almost always turbulent flow. Okay, and C, what is it going to be a function of? Okay, let's just try to figure this one out in our mind. Okay, C is going to be a function of primarily what?
The diameter of the pipe.
Yeah. You put a straw, there's going to be a big pressure drop. You put a big old pipe diameter, there's not going to be much pressure drop. Okay? So C, which is kind of inversely proportional to diameter, okay, it's definitely going to be a function of diameter of the pipe. What else?
A smoothness of inside of
Huh? No, that's not the next on the order. If I've got a pipe that's 1 meter long, or 100 meters long, or 1,000 meters long, or 10,000 meters long, right? The total pressure drop, it's the total distance traveled in the pipe. So I'm going to call that length of travel. That's the next most important. Well, what else?
it is going straight or if there is some bending.
Okay, but that we can take care of with the length. The trajectory, I'm going to take care of with the length. Geometry could be an issue, but we're looking at wells that are more or less straight up. It could be angled, but I'm just going to say that the geometry we build into that equivalent length. As far as that goes, the tubing theoretically could be larger at the bottom and smaller at the top, and we can create an equivalent average diameter. But okay. Well, the inside, the roughness, if the pipe is smooth on the inside or rough on the inside. So I'm going to call this, they usually refer to it as epsilon. That's kind of the roughness of the pipe. Okay? That's mainly it. That's what the constant is. And it's not proportional with these,
Sorry.
but yeah.
What about the viscosity of the fluid?
The viscosity of fluid, but gas in general doesn't have a big variation of viscosity. You know, that's the most boring thing you can deal with in PVT, because it's like 0.015 to 0.25. So it's not varying very much, but it's in there. The viscosity needs to be in there, so I'll put it in there. But the variation from case to case is not too great. And also, I think the Reynolds number takes care of that, because you got the Reynolds number, friction factor, and that's taken care of in that. So what we can say is that, well, I'll leave it like this, but basically these two together give the Reynolds friction factor.
So maybe the percentage of the liquid that comes from coming from gas.
Okay. If you have liquids with it, then that could cause extra pressure drop. But we're just saying dry gas. Just make it simple. Okay? Okay. Now what we're really interested in is the pressure drop from here to here. Okay? Now the problem is that we've got the pressure here may be, you know, this, what we call true vertical depth, That's not necessarily the same as L, because it could be a well like that. But the true vertical depth here, which maybe I'll give the symbol H. I don't remember what Fetkovich uses, but just call it H, total height. Could be kilometers, many kilometers. So the density difference between PT and PWF, because of the density of gas in this very long, vertical depth, has to be taken into account, because this equation only applies if these pressures are at the same level. So we'll take a break, and after the break we'll talk about how do we bring these two pressures to the same depth datum. Okay? So take a break.